If everybody could take their seats, please. All right, we'll get started. This will not be a long introduction. Our first speaker, quiet please, quiet please. Our first speaker is Daniel Harari from the Weizmann. He's going to talk to us about the digital baby guiding learning by innate structures. Listen and learn, Alfonso.
Okay. Can you hear me? Yeah? Okay, good. So if you stop hearing me at some point, just wave and I'll use the other microphone. I thank the organizing committee for inviting me. I'm really excited to talk about my research. And I think most of you are from backgrounds that relate to cognitive science and neuroscience, while my major discipline is computer science and artificial intelligence. So I tried as much as I can to bring you the higher level intuition about my work, and I managed to build a presentation which doesn't have even a single formula, so I hope you can survive this. I want to talk about, as an AI person, about a system that starts from visual sensation and ends with visual perception. It doesn't have any world knowledge. It can observe the world around it and gather some experience, and through that experience, develop representations of various concepts. So if you think about it for a little bit, it sounds like this is very much goes along the empiricism approach. But if we consider the slightly different interpretation that Alfonso suggested yesterday, if we combine this intelligence system structures within the system that allow the learning of concept through experience, then actually this is might be a nice compromise between the nativism approach and the empiricism approach, because you can then learn almost anything from the environment using this structure. So let's go through some examples from humans about early acquired visual concepts. It was shown that between the ages of 2 to 3 months of age, infants are able to distinguish between occlusion, when one object occludes the other, and containment, where one object is inserted into another object. Around the same age, infants start to follow gaze direction of other people. And not much later, they can actually recognize hands are as agents of change. So I'll explain later how we use these empirical knowledge about the development to suggest some models for the computational learning behind this acquisition. As an AI person, I have to present the current approach for machine learning with a kind of an relation to vision, which is my favorite domain. So you probably all heard about the deep neural networks that once are given very large sets of annotated examples, are able to learn a lot of tasks. Here you see some high-level visual tasks like image categorization, segmentation, depth and detection. And there are more and more tasks that these networks are able to solve, and some of them are even already kind of superhuman by means of performance. However, what happens if you don't have that much of labeled examples, which is probably what babies have? So they only have their own ability to observe the world. They have poor communication by means of language and interpretation of the surrounding adult environment, but still they are able to learn and acquire a lot of visual concepts, and some of them are pretty complex in the first year of life. So I will go through several examples in order to demonstrate how can this be learned according to our belief. And so the first example will be the acquisition of depth layout, or in particular the figure ground segregation. So how can a system that does not accept external guidance of images having some pixels labeled as background and other pixels labeled as foreground can learn to distinguish between the figure object and the background object? It doesn't know anything about the semantics of the objects or the background. So how is it possible? So we know that adults have a great capability to segregate objects even in a very crowded scene like this. Children also have this ability, but it's a developing ability, and actually when they are born, they are not that good at it. So how does it emerge? So we believe that it all begins with motion. So we are born with a good ability to analyze the optical flow that is extracted from temporal dynamics of the visual sensation. And as you can see, this can be used to use some segmentation. And it was shown that young infants are specifically sensitive to common motion. So if things, even if they look different, move together, they are usually grouped as a single entity, a single object. And another sensitivity is to motion discontinuity. So we're able to detect boundaries of motion discontinuities. This ability was shown to appear in infants as young as 1 and 2 months of age. So we suggest a model that starts from analyzing videos in frames in motion and ends up with the ability to segregate figure in static images. The model goes through 2 paths of processing. One is using motion discontinuities and creating some local occlusion boundaries representations. And the other one look at common motion and the grouping ability to create some form of objects, or let's say more contiguous regions in the images, okay? So the local boundaries are more general. They can generalize through novel objects and novel backgrounds, while the global appearance on the right is more object-specific or region-specific. And what I mean is that we don't need to actually recognize the type of object, but in a very short sequence of video, we can recognize the same instance of the object that was shown. So the model is presented with this kind of videos, no labels, just seeing these kind of videos. And we try to challenge the system with backgrounds that are pretty similar to the objects by means of appearance. And we use the capacity of motion analysis. So this is the result of motion segmentation based only on the motion. And you see it's not perfect, but we already get some regions that are in the figure in the foreground, some regions that are in the background, but also some regions that are unknown to the model. It doesn't have to be perfect, and infants don't have perfect abilities. Once we have this motion segmentation in a single frame, and we have this for many frames, for a single frame, we can extract local patches around the boundaries of the motion. Okay? And we usually try to select regions that have less unknowns, just to have better examples. And for each of these patches along the boundary, we associate a direction for the figure direction. Okay? So this is only based on the motion. Also, on the other processing level, we extract a snapshot of the pixels that are in the foreground. Okay? So we have these two patches and some regions. From the patches, we create a dictionary of informative patches. Okay? And these patches, as I said, are associated with the direction of the foreground along the boundary, usually in the middle of the patch. Interestingly, these patches include some very typical boundary features that were found useful for humans in separating objects from the background. This is a behavioral work by Goes and Palmer, and they identified mainly 3 types of occlusion cues. These are T-junctions, convexity, and extremal edges. And I think that most of you can recognize in each of these small patches which is the part of the foreground and the background. So interestingly, our model was able to extract automatically this kind of features just from these motion boundaries. And for a given test patch, then classify where is the figure side and the background side. Let me tell you that in our implementation, we actually normalized the orientation of the patch using the maximal directional gradient along the middle of the patch. But this was just because we used a small number of extracted patches, 100,000 of them. And if we use much more, which are available since these are all internally labeled by the system, we can actually dismiss this constraint. So we get pretty good results. And when we apply this to every pixel location in the image and aggregate the figure ground results for each pixel, we get for an entire image something like that. So it's a map. The red pixel indicate a high confidence level for foreground side, and the blue is of the background side. But as you can see, we get nice indications of the foreground and background sides, even on some regions that are on the object itself. But we also get some noise in the background. So this is not enough for the segregation. So that's why we look at another capacity that infants have. This is the ability, once we have the prior knowledge of some familiarity of a region, it will pop out. Can you hear me? Yeah, okay. So we collect a lot of examples from the video, and this can be maybe like a 2-second video. It's not very long, but it's enough to extract some examples of the foreground region from the motion segmentation. And we use this example to train an object detector for this region, okay? So once we are presented with a new instance of this region, even if it's on a different background, we are able to roughly detect the object in the image. If we now combine both the local boundary information with the global form, we can get much better maps that are both able to locate the interesting region of the object in the scene and also have very fine definition of the boundaries of the object. And if we use this to segment out the object, we get results like this on the left side. And if we use just the same segmentation algorithm without these cues, this is what we get. So this is on the right, it's only based on appearance. And this is based on the segregation cues that we got. So this demonstrates the ability to learn this segregation capability without having any labels from an external source. Let me now move on to another task which is related, and this is the ability to discover a containment event and discriminate between objects that are simple in the sense that they cannot contain other objects or containers. So computationally, this is a very challenging task because containers can be of various appearances. The variability is very high. And also there are some subtleties. For example, in these examples, you can see that the appearance is quite similar, but since there is no opening here, this is no longer a container that is available for performing a containment event. As adults, we may still call this a container. We may classify it as a container, but at this point, it cannot contain other objects. It has to be transformed. This is an example from empirical tests on 2.5 months of age infants, where the sequence of test events has this sequence of images. What you see here is that the container is first presented to the infant, and then 2 events may occur. The first one is that another object is behind it. The object is inserted inside, okay? And the two things may happen. One, when the container moves to the side, the object either the object always is there, but this is for an occlusion, and this is for containment. And it was shown that infants were highly surprised when this event happened, so they expected the object to be transferred with the container when it moves to the side. So we kind of looked at the empirical evidence and built some kind of a timeline for the developmental path related to containment. So as I showed, at 2.5 months of age, infants are able to discriminate between dynamic events of occlusion and containment. And later on, around 4 to 5 months of age, they are able to do it with they are able to detect the from high angle, and I will show what's. And only later, almost around 1 year of age, they are able to detect a support event. Okay. Interestingly, depth cues come only start to emerge only at this age from binocular. So this is probably not the most important thing for this computation. So we suggest a model that actually follow this trajectory of learning. We first have dynamic containment, then the model is able to discover containment events in static images. It is also able to measure the looseness or tightness of the fit, and finally it is able to recognize containment from high view when the simple object that is being inserted into the container is actually not being occluded by any parts of the container. We have some predictions for the cover and support cases. I will talk about it. So to give you the intuition about the computations behind it, let's look at some examples. So in a simple occlusion, the simple object is either occluding the container or is being occluded by the container. But when a containment event happens, the simple object first occludes the container, but then is being occluded by the container while still occluding part of the container. Okay, so this is a paradoxical occlusion, and we came up with this kind of a learning scheme that actually imitates the process that infants go through. So there is a familiarization phase when the system can observe moving objects that are going to participate in the test. So you can think of it as an introduction of the objects to the system, but there are no external labels whatsoever. And then the testing phase present objects with some relation to another object. So the model assumes these capacities at the beginning of the process. And these capacities are known to be found also with infants almost from birth. So as I said before, the computation of motion flow, the ability to group regions and segregate them from the background, and also the ability to analyze boundaries, and especially around motion discontinuities. So these are the test events that the model sees in the dynamic stage, and it has to discriminate between in front, behind, and inside. So the first capacity actually analyzes the optical flow, as can be seen in the middle frame, and extract some figure ground segmentation as in the right frame. The second capacity is able to discriminate in a static frame between the two regions, okay? But this is, you can see here that this is what actually the model knows. So the objects are a bunch of pixels okay, that can be discriminated from the background or from each other, but no more. The other thing, which is a most crucial capacity, is the ability to detect the ownership of common borders along the motion discontinuities. So this scene is the other way around. This is the motion boundaries from the simple object that is being inserted. These are the detection of the two regions. And here you can see the boundary start interacting with the other object. So in this case, this is a simple occlusion. The boundary always belongs to the blue object. So what happens in a dynamic containment event is that compared to the case of a simple occlusion where the boundary belongs throughout the whole event to a single object, in a containment event there is a switch. At some point the boundary starts to belong to the container rather than the simple object that's being inserted. So a mechanism that is able to detect the switch, okay, this is the cue for learning, the paradoxical occlusion event. This can trigger the attention for this event and discriminate it from the other occlusion options. Once we have this stage, we are able to discriminate the events in dynamic stages, in dynamic scenes. The model goes through some kind of maturement and has increased capacities. In this stage, we are able to extract internal boundaries along the motion discontinuities. As you can see here, this is the optical flow, and this is the ability to have some detection of the internal boundary of the container. And this happens only with containers, not with the single objects. Once we have this capacity, we're able in static images to discriminate between simple occlusion and containment, also by detecting a paradoxical occlusion where we have a combination of ownership along the common borders. At this stage, we are also able to measure the fitness of the object only by analyzing the boundaries along the internal discontinuity on the rim of the container. And this is known also in infants to occur around the stage where static containment is discovered. A new capacity that we need in order to go to the next stage is the actual ability to discriminate within a container between the front region and the back region that are being separated by the internal boundary. Okay? So when we include this capacity in the model, we're able to move to the next stage when we recognize a containment event even with a high angle view, although the container no longer occludes the simple object, so there is no paradoxical occlusion at this stage. However, if you think a little bit about it, in real life, the two views, the low view and high view, may be really temporally related. So a little change in the viewer angle may switch between the two stages, so the system will be able to move from one representation to the second representation pretty easily without external influence. One prediction of the model is that at an early stage, the high view containment may be confused with in-front relation until the ability to separate between the front and back regions are inserted into the model capabilities. So we get pretty good performance results on our test events. And I want to say a few words about the predictions about cover and support, because these are interesting cases. Intuitively, it seems that cover is the same as containment. But if you look closely, in these cases, you actually don't see the rim of the container. And we predict that if infants are shown this kind of events without presenting them first the internal side of the container, they will think that this is a simple occlusion. There are some empirical tests that were done with cover events, but in all these tests, infants were shown that the container has an opening, and only then they were presented with the event. Another prediction is about support, which looks kind of a simple thing, but actually if you analyze the motion information and the motion discontinuity information, you can see that as we simulated here with artificial boxes, there are no motion discontinuities along the edges of the closed box. So this is much more difficult computationally to detect that the one object is being on top of the other object rather than just being adjacent to. And indeed, this ability was detected was shown to appear in infants only late at the age. Okay, so the last thing that I wanted to show you relates to the ability to recognize hands, and I mean hands, the palm of the hand. And a related ability is to predict the direction of gaze of others. There are two related, and I'll show you how. So again, from empirical evidence, we know that infants are sensitive to hands as agents of change. And what this means is that when there is an agent that is approaching some object and does some manipulation on the object, infants are sensitive to the agent, the identity of the agent that is related to the change, rather to the appearance of the that is being manipulated. So we defined again some kind of a guiding signal called a mover, and the mover computationally is defined as a moving region that changes the static ground. This is a demonstration of a mover event. There is some optical flow going into a region, and after the flow is being out of the region, there is a change in the appearance of this particular region. We don't need any ability to recognize the actual object that is going into the region, or to know anything semantic about the appearance of the region. We just need to memorize for a very short period the appearance as it was before the motion entered the region. So here you see that we kind of split the image into some rectangular regions. We analyze the optical flow, and for a particular region, once the flow comes in, we memorize the appearance as it was before, and we compare the appearance once the optical flow is out of that region. If there is a change, we detect a mover event. Okay? So the motion was actually doing something active on that region. So with infants, it happens to be a very strong cue for detecting hands. The environment, if you think about it, most of the active agents in an infant environment may be related to hands. And here we recorded some videos of hand interacting with objects when there is also general motion in the scene. So the detector is able to detect only the mover events and not detect just add any other motion in the scene. And as you can see in a short while, even when the ball that is captured as a mover, it fires too. So if we use these events in order to act some patches around the center of the temporal events, we can use a classifier to train to discover the main appearance that appears in these examples. We can use some more examples just by using tracking from this center of event, so we can get some more examples. And we then test this classifier on two types of videos. One which is more similar to the mover extraction pose when people manipulate objects, but the other one is just moving the hands freely in space and changing the pose. When we test on these videos, results in red. So what we see here is the precision, the hit rate, versus the recall. The mover detector performs really good for manipulating scenes, but what you can see here is interesting. It seems at first that this is a very poor performance, but for a very small recall of events, the accuracy is very, very high. So this means that a model that relies on the best detections that he has with the best confidence, it's really reliable. It can use this example to train a good classifier, at least for these examples. The other colors just show you what happens when we use, instead of mover events, other sources like informative fragments or just general motion patches. So in order to generalize to other poses of the hand, we use another capability that is available to infants, and that is the ability to relate to a reference face, which is around the manipulating hand. So if we have, for example, this appearance already familiar to the model, we extract and we want to learn a new appearance. We first extract some kind of trace along the body, the body context from a reference face nearby. And then in a test image, we use the same path from the face to detect the hand region. And then we can extract the new appearance, okay? Just following, so the model at this stage is familiar with this trajectory of features from the face to what it assumes to be a hand. This is what happens here. And then when it detects the last point in this trajectory, it extracts a new example of what he now believes to be a new hand. So from a known appearance, we get new appearances using the body context through the face. If we do this co-training, when we use local appearance and context information, which is also known to be available for infants, we can actually, after very few such iterations, get this green graph in the performance graph here, which is quite high, especially if we consider the red here as the best that the model can provide using supervised examples. And this is surprising, just after 3 phases of this co-training. So again, this is an example of training without external guidance, just using the cue of the mover as a guiding signal for the system to learn. A related topic is trying to learn gaze estimation, and I will show you shortly why this is related. When we want to analyze other people's gaze direction, we want to associate a direction. Yeah, okay. We want to associate a direction with the face that is being shown. And infants, as I said, are able to do it pretty early. So if we consider the nature of humans, when we move objects, we actually attend to the object just slightly before the actual move. And if we use this cue, we can associate with mover events the direction of a face that is nearby and the location of the event. If we use these examples as training for a classifier, we get very good results. Here are some examples when we compare this kind of classifier in red with human predictions in green, when they are shown these kind of images of faces. And this is a performance graph which shows that the model, which is in red, gets pretty good results compared to the supervised and the human subjects. So here is a demo of the abilities that were acquired without any external guidance. So you can see in red the mover events, then the detected hands, and the gaze direction. Now, it may be that at this stage, the gaze direction is mainly using the head orientation rather than eye gaze, but this is also known to be the case with infants. And actually, we extended the model later to have a really fine ability to use also the eyes, and we use depth information to extract now 3D gaze rather than 2D gaze from 2D images. This is very useful when we want to analyze scenes by means of social intelligence. And in this example, we want to discover joint attention. So we combine the ability to extract 3D gaze from 2D images with some estimation of the depth in the scene and some segmentation of regions, coherent regions in the scene. And when we combine these three sources of information, we're able to discover in all these scenes cases of joint attention where there's a common target versus events where there are different targets. So this is very useful for understanding social scenes. So we can think of the learning trajectory in this sense that we can actually learn a lot of complex visual concepts just by going with these abilities of using internal cues to get more and more concepts from experience. And I'll summarize first that we saw how models use these internal cues to learn the concepts automatically. The models can also provide reasons for the human development trajectory, which is sometimes very peculiar and not very intuitive. And I think that, interestingly, as I showed before, the current learning methods cannot explain these learning abilities, both in infants and also without supervision. So I will remark that this mechanism of internal supervision can serve actually a few useful and general roles for intelligent systems. So first, we don't need to use so many examples, which are sometimes very unnatural. But then we can also allow the system to acquire concepts that may be very subtle in the environment, but they are very meaningful and crucial for the observer itself. And this can be done by having these internal structures created in the system through evolution, for example. And these built structures can also provide us with capacities that can guide the learning process rather than use explicit representations. What I mean by that is that the structure does not have to actually encode the final concepts, but they actually frame the learning process in order to allow the system get to the specific concepts by experiencing and observing the world. Okay, so thank you.
Thank you very much, Daniel. Questions?
Thank you. Very interesting and very impressive. I like this is what's required to be a containment event and so forth. I guess I had a general question. The performance of your algorithms was very impressive in a lot of circumstances, but of course wasn't completely equal to humans or 100% correct, which would be unsurprising. But what do you do with those differences between human and algorithm performance? It could be that there's some uninteresting reason for it. You didn't have quite enough training examples, or something about the network wasn't quite right. Or on the other hand, it's conceivable, I guess, that there's some in principle limitation of the algorithm such that it's going to fall short of human performance, or it's going to fail in particular ways that humans don't fail, and that would have very different implications, I guess. So,
right, so
can you say anything about that?
Yeah, so the main goal was actually to demonstrate the ability to learn about this kind of concepts. We didn't aim for a very good performance by means of the results, but it turned out that they came pretty good. Still, when we compare this to humans, humans have better abilities, and we don't say that the implementation of our model actually uses the exact same computations that humans have, but we rather look at this as if we use some much primitive and simpler computations, we still are able to extract the information that is needed to learn about these concepts. Otherwise, it doesn't seem conceivable even to try to extract the information that is needed to learn anything about this concept. But as you say, there's still a gap between the model performance and the human's performance, and I think if we try to maybe look at specific computational processes in the brain, and maybe use neural nets that come closer to human abilities as I showed before, we can try improve the performance of the existing models.
Well, let me pursue it just a little bit further. Have you looked at the failures? Is there anything systematic about them such that there's certain specific systematic things that the algorithm fails to do? And would that give you any clues as to how it could be improved, or how it could, if you're trying to model human performance, how it could more accurately model?
Yeah, sure. We are definitely looking into the failures and the errors too. Let me give you an example from the gaze detection algorithm. So what we noticed is that most of the information that this model captures is taken from the head orientation rather than the eyes. And if you actually present images where the eyes are looking in a very different way than the head orientation, this model cannot cope with this. And when we investigated it a little bit further, we saw that actually the processing in the brain has these two mechanisms that extract information from the head orientation and then corrects the gaze using the eyes, the offset between the eyes and the head orientation. And at the next stage of our model, when I showed you the 3D gaze estimation, which is much more accurate, we actually use a two-stage processing, which first extract the head orientation and then only then copes with the offset from the eye gaze and use a different representation of the appearance of the eyes rather than just a global face. So this is an example, but we also analyzed other things related to the containment, and we're working on it.
I have a question, because one of your introductory slides, you showed the deep neural networks, and you showed, okay, there's those labeled images, but we don't, as humans, actually have everything labeled, right?
Right.
And this is the point where I'm not sure if that's true, because maybe the difference between your model and real infants is that you, as parents, keep talking and labeling everything.
Right.
So while there is those motion cues and everything, even as they're small toddlers and small babies, you start saying, oh, here's a choo-choo train, here's that. So how would the model be improved, do you think, if you would include some labels which are obviously there that are provided by the parents?
So that's true, and as you go along, as the infant is growing, it gets more and more input from and guidance from the environment. As you saw, for example, from the mover detector, it first had a lot of noise captured within the initial examples. So once you allow some external guidance to cope in, and you can eliminate some of the noise, of course the algorithm will learn much better model for the appearance and will make much less mistakes. And in the pipeline, in the code training process, it will of course boost from these more pure example sets. We focused actually on the very early stages where the infants can't get much even from the guidance of the parents, because they don't understand the language and they don't understand the meaning of pointing and presenting. But of course, later on it can improve. Yeah.
Question at the back.
That's my seat anyway. Hi, very nice talk. The other thing, sort of similar to this, is the difference between, robots and babies is that babies self-construct information. Visual knowledge, conceptual knowledge happens when they start to interact with objects, and I was kind of wondering if you would, implement that in your models.
Yeah, so that's true that this model did not include the interaction, the active interaction of infants with the environment. But this is actually a bit later in development, right? Because the beginning, like until the age of 6 months, the infants are not willingly manipulating the environment. I mean, they have pretty limited motor skills and control. It's more like they happen to do stuff. They can hit things and they can learn a bit about the environment. So this is, of course, a good source of information, but still it is internal. It's not having an external labeling. They can interpret this information as they go along. So this might be related to a different type of learning, reinforcement learning, which you get feedback from the environment, but you can interpret this feedback as a positive reinforcement or a negative reinforcement, and the model can cope with both types of reinforcements, but the result will be different, right? So we didn't deal with this in the model, but indeed, as the infants grow, they use more and more of this kind of information, aside from the external guidance that they get from adults.
Alfonso?
The objects that you used were rigid objects. What happens with soft objects? What happens to the transformations that occur within an object when you grasp it, when you move it, and so on?
Right. So actually, all the objects were kind of soft. I mean, for the container, there were these stuffed animals, which are quite soft. But I don't think that the distortions of the objects at this level are being captured even by this motion analysis algorithm that we were using. It's very subtle, and I think that it almost didn't affect the shape. But if you try to think about it, these distortions can actually influence in two directions. First, the global shape might change a little bit, but the model doesn't care about this. As you saw, for detecting the object, we actually extract different instances of the object at different poses and stuff like that. So the classifier is quite robust, but it's also very crude detector. And the other thing is that the local appearance may change due to light conditions and stuff like that. But again, since the detection is so rough, it doesn't affect the global performance of the model. We are not relying on any fine appearance details. Yeah.
Any other questions? Oh, lots. Okay. I won't ignore this side of the room, sorry. Yeah. I'm going to go there in a minute.
Can you explain to me again this distinction between internal and external signals?
Okay. So what I call external signal is when you provide an example, like an image, and then you provide also some annotated information or label about this example. For example, if I show you an image of a horse, and I give you a label, there is a horse, so this is one kind of external information. The other thing is, for example, for segmentation, if I want to segregate between objects and I give you a mask where I show you that all the pixels in this region are labeled as 1, and all the pixels around it are labeled as 0. This is another example. So with internal guidance, you only get the input to the system is only the video or the image without the label or the annotated mask. And what I mean by internal guidance is that the system has some rules for the learning that it can generate by itself these kind of labels.
I understand, but from the point of the infant, does this distinction make any sense? I mean, if it starts kicking at 3 months for objects, and it just gets feedback, that's all, right? So this distinction between internal and external that you apply in your analysis, for the infant, it's the same. It's the world giving feedback.
Okay, so this is related to what this lady mentioned, and this is true when the infant is able to interact with the environment and record some sensations from this interaction. Again, I'm not talking about this kind of learning in our models because it is more it appears only later in the development, not at the very early age of 2-3 months of age, right? But even then, the system needs somehow to overcome the interpretation of these interactions, because hitting some object can say that indeed there was some force that was recorded back from the environment, but the infant can interpret this as the object may move if it hits it, or it just hurts, or whatever. I mean, the interpretation of the interaction may be complex by itself, and if the infant just uses this information, it might not suffice to learn much about the concepts of the environment. So if you combine the two mechanisms, this might yield better models.
There were some questions over here. This one, just over here.
So I'm thinking back to the nativism empiricism debate and also the discussion about congenitally blind individuals yesterday. So if these are innate structures or computations, then how would these computations be adapted by other modalities in the case of, for example, congenitally blind individuals?
Yeah, so we thought about this, and actually when we looked at for example, in containment and figure ground segregation, it turns out that blind also have these concepts of things that are being in front and behind, and things that are being inserted into other things. So they might use different modalities to construct the information. For example, they can sense the rim along a container, and then they can understand the concept of some kind of paradoxical occlusion, by means that some object is maybe in front and behind the same object at the same time. So this concept can emerge using different modalities. They might emerge at different ages, though, because you need the motor skills to detect these features, these discriminating features. Yeah.
Other questions? Yes, over here.
Thank you very much. Very, very interesting. I have a question related to whether you ever compare in detail the quality versus the quantity of the training experience. Let me explain. Here, I understand very well why you present messy images, because you want to simulate what infants get as an input. Mm-hmm. But from the point of view of seeing whether, if you wanted to boost learning, make it quicker and better, would it be best if we really start off with the mechanism that you are simulating here, giving plenty of messy examples, or a few very purified ones, let's say with geometrical input and devoided from all the unnecessary supplementary information that in the normal environment we get? So
we actually tested with some of the tasks this direction, and surprisingly, or maybe not surprisingly, this didn't help much. So for example, for containers, we collected a very large data set of containers and provided external labels for containers and non-containers, and then we try to classify using like the regular classifiers. This didn't work very well. So the variability in the appearance is too large in order to already capture these concepts. And when you use this learning cue of the discontinuity along the rim, this is a very, very strong signal that is actually better to cope with the variability in the appearance than just providing more and more very fine labeled examples. And similarly with the segregation, it also was the same thing. And when we provided better segmentation images, we came up with the same boundary dictionary. So as was with the unsupervised training. Yeah. So.
Another question? Another question from Mike?
Yeah, this is kind of a specific question. I was thinking about containment a little bit more in your high view. Mm-hmm. I would imagine you could have something similar with respect to your occlusion relationships in the high view when the object is actually in the container versus above the container, but still, perception line. Right.
Right. Actually, we don't know. I'm not familiar with specific experiments. But we think that even adults may find this kind of situation somewhat confusing. It really depends on very subtle cues like shadows, lighting conditions, and stuff like that. And when these cues are removed, even adults find it difficult to discriminate between these two static situations. In real life, you usually have the dynamics to help you out, and then you can resolve these situations using the dynamic information. Yeah. Right. Yeah.
Yes, Alex.
That's fabulous.
Yeah. Yes.
So, we appreciate that this is all motivated from the developmental literature. I was just wondering what sense you have about how many of these kinds of innate learning mechanisms there might be, and what are the constraints to decide what they are.
Yeah. Very great, and you. We believe that there are not signals, and these signals may be used for acquiring different models in some combinations of these signals, and also across different modalities. For example, the mover event is a kind of a temporal singularity input, and it can also be used maybe in sound, speech, and things like that, in order to discriminate between like static noise or some harmonic noise and specific speech or sound that has some kind of a semantic structure, but we don't have a sense of how to extract these cues currently, and that's why we are using empirical experience. But we don't think that, although this seems to be very domain-specific cues, we don't need such a cue for any concept to be acquired. The tree that I showed before shows how you can combine then later several of the learned concepts along with the signals to acquire more and more concepts which are more complex.
All right, I think we'll have to end the question period and thank Daniel very much. So now it's coffee and posters, and please be back here at 11:15 sharp. 11:15.